Welcome everyone. Today we are talking about the definitions part of Proposition 14 of Gottfried Wilhelm Leibniz's work on the arithmetic quadrature of the circle, ellipse and hyperbola. And in this very definitions part, Leibniz is making, as it says, some definitions, especially with regards to analytical curves. And what this is all about, we're going to see right now. So we start off with a simple curve of a paraboloid type. And Leibniz said that if you assume to have some points on the curve, and if you are actually searching for these points and you want to know if they belong to this very curve or not, then you can treat these curve as analytical expressions. And only if the curve is actually to be expressed as an analytical expression, then also the curve can be called analytical. And he says that an analytical expression or an analytical calculus which defines the curves is only analytical if the problem of this curve or finding the nature of this curve such that you can determine its points are transformed into treatable problems by means of this very what he called exact analytical calculus. And if you have this analytical calculus, you can treat the very properties of these points and the entire curve as unknowns of an equation. And this very equation he refers to as the exact analytical calculus. But for doing so, and in order to make up an exact analytical calculus for a curve, which again enables you to determine the points and the locations on this curve, he needed to make some definitions. And he started off with what he later called the parameter P. And parameter P is basically this distance between the very origin of both of the axes. So this is the conjugate axis, and this is the axis, this is the conjugate axis, just as we determined in previous propositions. And P is the distance between the origin point A and a point pi, which you place on the axis. He further defined the distance AB, which he termed y, and nowadays this is reflecting the abscissa. And he also defined the distance BC, which is the ordinate of a point C in this case. And he also introduced some value or some quantity in terms of the conjugated abscissa. So you have the abscissa AB here, AB, and he also introduced the conjugated abscissa as AB emphasis, which is basically this one, the same distance AB, but just put onto the conjugate axis. And this is useful for some of the constructions we are going to present in the following. So in this case, we have a curve which is a simple parabola. And by use of these definitions, we now can draw actually areas which represent the very nature of the analytical expression. So a parabola is basically expressed by this very analytical expression. Namely, on one side of the equation you have the abscissa y and the parameter P, which is this rectangle, the green one. And on the other side of the equation you have the square of the point's ordinate, which is this one. So the nature of the parabola is such that if I now change the pi handle, I of course change the look of the parabola because I either stretch or skew it, and my areas are changing their shape according to this analytical expression. But we know due to this expression that the area of the rectangle and the area of the square are always the same, because this very relationship is what actually defines the parabola. And this is a totally different representation of what is introduced in schools in terms of functions, especially in relationship with coordinate systems or Cartesian coordinate systems today, that the length and the distances which you apply there are actually standing in a certain relationship. And this is often forgotten because the way the Cartesian coordinate system is used today is very tempting in terms of quickly forgetting about these relationships. And as we go on, we can also introduce another handle, a B handle here, where we change the actual location of the point C on the curve. And as you see, according to this analytical expression of the parabola, it is clear that I change the length of the ordinate by changing the place C on the curve, and hence I also change the size of the square of the ordinate, which is the red one here. But again, since the rectangle, the blue one, namely p times y, is also made up by the distance of the abscissa, like AB, which in our case we now use as AB emphasis, which is the same length as AB because we explicitly defined it this way. This also changes when I change the location of the C point. And in any case, it is given due to the analytical expression that the area of the rectangle and this red square are always equal. And this is what needs to be considered, because, yeah, as I said, ever since the Cartesian style of depicting things, especially what is termed today as functions, quickly leads you into the road of forgetting about principles and only looking at quantities. But as I said, the quantities which you depict in a curve are actually made up by multi-dimensional objects. In the case of the parabola, it's two-dimensional because you have the ordinate, in our case v, and you say that due to the analytical expression that v square is equal to p times y. And if you consider today's representation of a function where you would only say y equals v square, and you have y as a quantity and v as a quantity, that doesn't actually give you a representation where you match the dimension of both sides of the equation, because for that you actually need a parameter, because if you cannot compare a length to an area. So this qualitatively aspect of an object Leibniz maintains with this very set of definitions and his very viewpoint on how Descartes looked at these things, because Leibniz basically took from Descartes what was useful in terms of the coordinate system, but he really made sure that the definitions and the relationships in terms of the dimensions and the several lines toward each other are not forgotten. So that's why he introduced this parameter p, because he said that if you use the p parameter to compensate for the missing dimension on one side of the equation, you can make sure that you actually compare areas with areas, or three-dimensional objects with three-dimensional objects, as we shall see in the next couple of representations. Like this one. In this representation we have a cubic parabola, and the cubic parabola is basically made up of the analytical expression that you have on one side of the equation a quadrature, which is made up by the square of the parameter p, and y, so the abscissa. So as you see, the front side of this quadrature is basically the square of the parameter pi, and the length of this quadrature is determined by the abscissa. So if I make this once more visible, so the abscissa is determined by the distance AB, and AB emphasis we now just conjugated sort of into the plane in order to get a bodily representation of both of these three-dimensional objects. And on the other side of the equation you again have our cube, made up of the cube of the very ordinate BC. And the nature of the cubic parabola is such that its points always meet this criterion, that the body you make up of the square of the parameter and the abscissa is equal to the cube of the ordinate. And this becomes clear as I move both handles, the parameter and the B point or the B handle, where I just change the abscissa of the point C and hence its location of the point C on the curve itself. And another thing needs to be noted here quickly is that the analytical expressions which Leibniz refers to always are built up in the same way, namely that the sum of the exponents of each term on each side of the equation is always equal. So he really uses this parameter p to make sure that a body is compared to a body. Because if you would look only at the abscissa, like y, like this one, this cannot possibly be compared to a body like v to the cube. And hence he maintains consistency in terms of the dimensions, something which nowadays, as I said, with the application of Cartesian style coordinates and the very thing that we term as functions today are often forgotten. And this is gonna be applicable for every type of paraboloid. So as a cubic parabola is paraboloid, you see that the relationship is such that the cube of the ordinate is the same as the square of the parameter times the abscissa. And this is also holding for other types of paraboloids, as we shall see. But now Leibniz does something else very interesting. He says that the nature of the curve is not solely defined by its analytic expression, but also by a proportionality of different points on the curve. He says that can also be taken as the very nature of the curve. Let us say you have on this very cubic parabola 2 points, one which is determined by y1 and v1, and another one which would be determined by y2 and v2. And the equations or the analytical expressions for both of these points would be such as I'm pointing out here. So p squared times y1 would be equal to v1 to the cube. And also for the second point, p squared times y2 would be equal to the v2 to the cube. And therefore is that you could rearrange the analytical expressions such that you get proportions between the abscissas and the ordinates. And the ordinates being the v distance, so the distance between b and c, as we defined it here above, and the y distances or the abscissas would be the distances between a and b as we defined it. And you see, as you have arranged the analytic expressions for each point on the curve, you get these proportions, and you easily can eliminate the parameter. So there's p squared on the upper as well as the lower part of the fraction, and you get at the end y1 to y2 equals v1 to the cube divided by v2 to the cube. And he said this very relationship between the proportions of the abscissas and the proportions of the ordinates also determine the nature of the curve, in this case a cubic parabola. And is in this case called a cubic parabola because the ordinates, so the v distances, are standing, what he said, in a tripled relationship to the proportions of the abscissas. So you see you have expression v1 to the cube and v2 to the cube. That means the whole proportion v1 divided by v2 to the cube is equal to the proportion of the abscissa of point 1 divided by the abscissa of point 2. And that's why this one is called a cubic parabola, because this very statement that the abscissas or the ordinates have a tripled proportion in relation to the same proportion of the abscissas. And that holds true for any type of paraboloid, as we shall make clear in the next step, because in the next step we are going to go to look at what is called a sub-doubled cubic parabola. So the terminology becomes longer, but the principle is basically staying the very same. So you have again our analytic expression. It produces this kind of curve, and if you would like to determine a point on the curve, it can be done by the means of this very exact analytical expression. So we have the same definitions. Pi, our parameter, AB, the abscissas, or what we termed as the y dignities, then BC as the v dignities being the ordinate of the very point, and also we have again our AB emphasis, which is the conjugated abscissa, and in this case the abscissa AB emphasis is again relative to the abscissa AB conjugated, such that it is showing into the a set plane, if you will, or into the plane, in order to get the bodily relation or the bodily reflection of what we would like to show here. And why is this curve called a sub-doubled cubic parabola? We're gonna explore by means of the very same relationships in terms of the proportionality of the equality of abscissa proportions to the ordinate proportions. And the analytical expressions, both for both points are listed here again. So you have p times y squared equals v1 to the cube, and you have p times y2 squared equals v2 to the cube. And you again see Leibniz makes sure by means of the parameter p that the sums of the exponents on both sides of this expressions are equal. So you have v to the cube, so exponent is 3, and you have y squared, so the exponent is 2, and you have the parameter p where the exponent is 1. So the sum of exponents on this side is 3, and on this side also 3. Again, just to make sure that you really compare a body with a body, and that you're not comparing lines to a body or lines to an area, because that wouldn't work in physical reality. And if you go through the rearrangement of the proportions, you can again say that the p times y1 squared divided by p times y2 squared is equal to the proportion of the ordinates v1, v2, and all of that to the cube. And at the end you can again eliminate the parameter p on this side, and you see that your proportions now play out like this, that at the end you have y1 squared divided by y2 squared is equal to v1 to the cube divided by v2 to the cube. And that's why it's called sub-doubled cubic parabola, because the ordinates have a cubic exponent, and the abscissars have a exponent of 2. So cube because the ordinates have this exponent 3, and sub-doubled because the abscissars have the exponent 2. And this way you could make up many more different types of paraboloids just by the very principle of the analytic expressions as shown here. And Leibniz sort of summarized this relationship of analytic expressions in a little table, and where he actually states that the equations of paraboloids are single-term analytical curves as examples, and he says all these analytic expressions are paraboloids where the ordinates v for the abscissars y or their powers are in direct, simple, doubled, tripled, quadrupled proportion to the ordinates v or abscissars y themselves, their squares, their cubes, their quadrature squares. So when you see that you get different types or a grid of different types of paraboloids where the proportions of the abscissars and the ordinates are having a different exponent. And this is sort of true for much more of the paraboloids. So you basically could extend this table to diagonally down to the very higher orders, so any higher order you like, as long as you stick to the principle that you make up one side of the parameter p and either the ordinate or the abscissar, like here PV, 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 or the other way around. If you take the parameter to the other side, you can also PY, as long as you make sure that no matter how you arrange the exact analytical calculus, as long as the exponents of both terms of these expressions have the same sum of exponents. So as long as the exponents of this side of the equation is equal to the sum of the exponent of this side of the equation, or the other way around. And as long as you stick to this principle and make sure that you define bodies which you compare to each other, rather than taking the quantities of some lines and comparing it to another quantity, you can basically draw curves according to these expressions and be sure that it is a paraboloid. So let's go now to the hyperbola. So the hyperbola has a different arrangement as now in terms of the analytic expressions. So they're still analytical curves because you can express them with an exact analytical calculus or an analytic expression, as we call it here. So the thing with the hyperbolas is now that instead of having the ordinate on one side of the equation and the parameter and the abscissa on the other, or the other way around, you now have the abscissa as well as the ordinate as a term on one side of the equation, and p as a parameter with some appropriate exponent is on the other side of the equation or the analytic expression. And from this you can derive that the proportionality also can be stated with this type of expression. So because if you again imagine two different points on the curve of the hyperboloid, you can, by means of this expression, make up the equation. So like y1 times v1, which is always expressed as the very rectangle which you make up by the abscissa and the corresponding ordinate. So this is our red rectangle here. And this rectangle will always be equal to the square of the parameter, p squared, which is our blue square here. And as I change the pi handle, I change the parameter, hence I stretch or I skew the hyperbola, and according to that our parameter distance changes, so that changes the size of our parameter square, of course, but since it's also stretching or skewing the curve, it also changes the look of our rectangle, which is made up by the ordinate and the abscissa. And the curve is only a hyperbola or a hyperboloid if the two areas are equal. And since we constructed a curve this way, this is of course always be true no matter how I dislocate the parameter, or no matter where I move the point on the curve. And then going on, you could again put these two analytic expressions for both points into relationship to each other, and you can draw out proportions, namely that the proportions of the abscissas as y1 to y2 is now equal to the proportion of the parameter p squared times the ordinate v2 divided by p squared times the ordinate v1. And as compared to the paraboloids, the significant part now for the hyperboloids is that the relationships of the proportions of the abscissas and the ordinates is now reciprocal. So instead of having y1 divided by y2 is equal to v1 and some v2, you have it now the other way around. So v2 is now standing here on top of the fraction on the upper part. And this is inherent to the nature of the hyperbola, or because of that relationship, some people also term the hyperbola the anti-parabola. And again, you can eliminate the parameter p squared here in this case, and you again reach this very equation of proportions of the abscissas on one side and the ordinates on the other side. And it's only hyperbola if the proportions between the abscissas and the ordinates are reciprocal. So, but you could also, instead of having just the plain ordinate and the plain abscissa, you could also, with the hyperbola, now add some exponents to it. And this is what we're gonna go next to. In the next one, we look at a quadratic hyperbola. So this is what the curve looks like. And again, as you see that since we're going now through a higher order hyperboloid, that we now also need to compare objects of higher order. So in this case, we're now comparing a quater in red, which is made up by the y distance, so the abscissa, and the square of the ordinate. So we have this ordinate BC, and we make the square of it. This is giving us v squared. And if you compose the body out of these distances, you get this green quater here. And this, again, making sure that we have the same sum of exponents of both sides of the equations. This now we compare to the cube of the parameter. And the quadratic hyperbola is of this very nature, that this quater and this cube are always equal, no matter how you put the parameter and no matter where you place the point on the curve. So, and the proportionality is of course also true for higher orders of hyperboloids. So in this case, you have for the first point y1 times v1 to the square is equal to p to the cube. And for the second point, y2 times v2 squared is equal to the parameter to the cube. And therefore again, you would rearrange both of these expressions such that you get proportions of the abscissas, y1 to y2, and that's equal to the proportions being made up of p to the cube times v2 to the square divided by p to the cube times v1 to the square, eliminating p, and you have your proportionality relationship between the abscissas and the ordinates. And you see that the reciprocality of this relationship remains true because it's a hyperboloid, but now you see that the ordinates are standing in a doubled relationship to their abscissas, and that's why it's called a quadratic hyperbola. Alright, so I hope that it became a little bit clear in terms of the definitions part, that it is quite important to keep consistent in terms of what you actually compare when you draw the relationships between special lines and the curves. And Leibniz expressed this terms of hyperboloids also in a table, as he did before with the paraboloids. And you can also say now, instead of being in a direct proportion, the abscissas and the ordinates, all their powers are standing now in a reciprocal, symbol, double, tripled, quadrupled relationship to their ordinates or abscissas themselves, their squares, their cubes, etc. And this is how he defines analytical curves. And he uses these analytical curves to go on with his work in terms of the quadrature of the circle. And how he did this, or how he does this, we're going to go through in the next couple of propositions coming up. But it is always to be kept in mind that when he's talking about analytical curves and analytical expressions, that it is dealing with these kind of relationships, mainly between the proportions of the abscissas and the proportions of the ordinates. All right, so that was everything I would tell about the definitions part of Proposition 14. If you're interested in going into a little more detail, I recommend you go through the animated part of Proposition 14, or rather its definitions part, on this very website. So I hope you stay tuned for the next propositions coming out, and I hope you enjoyed it. Thank you very much, and bye-bye for now.